Automatically gives you a geometry on the projective space. So what this tells you is that philosophically the geometry of the projective space is controlled by the geometry of the affine space, and that is going back to Euclid, okay, philosophically. Yeah. Okay, so so let's recall that if you take a point in n-dimensional projective space and you take a polynomial vanishing on the line above that point, okay, in the affine space, n+1 dimensional affine space, then we saw that every homogeneous component of that polynomial will also vanish on that line, and in particular that polynomial will not have any constant term, okay. So it will be a sum of homogeneous components, and there won't be any homogeneous component of degree 0, alright. Now this leads into the study of what are called as homogeneous ideals, and when you try to translate from the algebraic geometry of projective space to commutative algebra, you end up studying properties of homogeneous ideals, okay, and the key to defining a homogeneous ideal comes actually from this observation. So let me explain that in more detail. So the first thing is the translation from projective geometry to commutative algebra is in the language of homogeneous ideals. And graded rings, okay. So this is a little bit of algebra that one needs to recall, alright. So recall the following things: the notion of a graded ring. First, a ring S is called graded, is called, well, graded, which is supposed to mean n graded, or rather whole numbers graded. Okay. If S is the direct sum of SD, d greater than or equal to 0, okay, with each S sub d an abelian group, an abelian in fact of course abelian, a subgroup, an additive subgroup of S and such that S P into SQ lands inside SP plus Q for PQ greater than or equal to 0. Okay. So under multiplication, so you see what is a here the W corresponds to whole numbers, which means that you include 0 and then along with the natural numbers which start from 1, okay, and this indexing is on the whole numbers, alright, and the ring should break into a direct sum of pieces. Each piece is a additive subgroup of the additive group underlying the ring, okay, and there is a multiplication in the ring. The multiplication should the multiplication of the pth piece with the qth piece should land you inside the p plus qth piece, okay, and of course you know well, if my ring could my ring need not have 1 if you want, okay, when I want to make a general definition it need not even have 1 and it need not even be commutative, and in that case I will also it also follows that SQ into SP will also land into SP plus Q by this, okay, and therefore the p piece, and if you take an element in the pth piece and an element in the qth piece and you multiply them, they land in the p plus q piece, okay. We say that this is meant to, this is also sometimes referred to as the multiplication preserves the gradation, okay, it respects the gradation, it takes a, so what you do is you think of elements of SD as elements as homogeneous elements of degree d, okay. So the elements of each SD are called homogeneous of degree d, okay, and what you are saying is that every element of the ring can be decomposed into homogeneous elements of certain degrees, and the decomposition is unique. The uniqueness of the decomposition is because of the direct sum, okay, the direct sum tells you, okay, that every element of S can be broken down, can be written as a sum of finitely many elements which are homogeneous, which belongs to certain homogeneous pieces, and for each each summand in that sum is unique for that homogeneous. So if you give me an element here, its for any d its dth homogeneous piece is uniquely determined. That is what the direct sum is supposed to mean, alright, and the multiplication preserves it respects the homogeneity in the sense that a homogeneous element of degree p multiplied by a homogeneous element of degree q leads to a homogeneous element of degree p plus q, okay. So this is the definition of what a graded ring is, of course, but so let me write this: elements of S D are called homogeneous of degree d. Elements of SD are called homogeneous of degree d, alright, and of course the particular case that we are interested in is polynomial rings and their quotients by prime ideals, their quotients by ideals which are homogeneous. Okay, so what is a basic example? The basic example is of course the polynomial ring in finitely many variables. I will take the variables to be n+1 variables because I am always thinking of projective space. So example, take S equal to k x0 etc. xn, Sd is equal to the subset of S consisting of homogeneous polynomials of degree d. Okay, and so you know that the whole polynomial ring is a direct sum of homogeneous polynomials of various degrees. That is just a reflection of the fact that you take any polynomial, you can break it down uniquely into homogeneous components, each component which is a homogeneous polynomial of certain fixed degree. Okay, and so this is the example that we keep in mind. Okay, and of course it's not just enough to work with this, but we need to also work with graded quotients of this. Okay, so for that, so it's a you know the intuitive idea is very clear. If you to get a quotient you have to go modulo an ideal. Okay, but to get a graded quotient, okay, you have to go modulo what is called a homogeneous ideal. Okay, so what is a homogeneous ideal? An ideal I in S which is graded, where S is graded. So I will draw a line here. Okay, I will draw a line here, and I am again going back to the old situation where I take a graded ring which is direct sum of homogeneous pieces. Okay, I should say it's a direct sum of pieces which correspond to homogeneous elements of certain fixed homogeneous degree. Okay, so take an ideal S, an ideal I in S. It's called homogeneous if I is I intersection SD direct sum D greater than equal to 0. Okay, so look at this definition of what a homogeneous ideal is. So the definition is, you take the ideal, all right, you intersect it with S sub D. Okay, when you intersect the ideal with S sub D, what you get is, mind you, not an ideal, because you are only intersecting with the additive subgroup, and you know the ideal is also an additive subgroup, therefore the intersection is again an additive subgroup, therefore each of these is an additive subgroup of the additive group underlying the ring S. Okay, and now you take the direct sum. Okay, of course it is a direct sum because all the SDs themselves are pieces of a direct sum. You take the direct sum, and that usually it's obvious that this will be contained inside I. Okay, the right side, every piece, okay, I intersection SD refers to all the elements of I which are homogeneous of degree D. What is an element of I intersection SD? It's an element of I which is in SD, but elements of SD are thought to are called homogeneous elements of degree D. So I intersection SD is those elements of I which are homogeneous of degree D. Okay, and of course if you take a direct sum of this, mind you, the direct sum, an element in the direct sum only consists of a finite sum, even though the direct sum is over a collection of infinitely many subscripts. Okay, so an element here is certainly here by definition, but the requirement is every element here comes from here. That is the homogeneity definition. Okay, so you know what it means. It means that in other words, if f is in I, okay, if you take f is an element of I, then since S is a direct sum of all the SDs, d greater than or equal to 0, what you will have is f will be f0 plus f1 plus etc. up to fm. Okay, you will get this, alright, where so you will get a finite expression like this. Okay, you get a finite expression like this because it's an expression in a direct sum. It will live only up to a finite index. Okay, beyond this all the fj's will be 0, right. So so here fi are in Si or fd is in Sd, you get a breakup like this. Okay, and so if you take an f and you break it into homogeneous pieces, then the condition is that this condition will tell you that each fi is also in f. Okay, so you see the implies that fd belongs to I for every d for every index d. Okay, see why is that true? That's because you see, take an f here, f is, because f is in I and I is in this graded ring, and this graded ring has this graded decomposition, f has a decomposition, alright, where each of these pieces are homogeneous of the corresponding degrees, alright. On the other hand, since you have written like this, f also has a decomposition here because of the equality. F belongs here, so it corresponds to an element here, so it also has a decomposition in terms of homogeneous elements. Okay, but both decompositions are to be valid in S, but in S there is only one decomposition. The decomposition in S is unique, therefore what it forces is that each fd is already in I. So the moral of the story is an ideal is homogeneous. Saying that an ideal is homogeneous is the same as saying that every element of that ideal, you take any element in that ideal, every homogeneous piece of that element is also in that ideal. One way of saying that an ideal is homogeneous is saying that you take any element in that ideal, okay, then every homogeneous piece of that element is also back in that ideal. Okay, and you see that is exactly a geometric, that is exactly algebraic reflection of this geometric fact. If a polynomial vanishes on a line, then every homogeneous component of that polynomial vanishes on that line. So what you are saying is that if the line is in the 0 set of an ideal, suppose you take the line to be in the 0 set of an ideal, okay, and you take an element of that ideal, that means that is a polynomial which vanishes on that line, then what you are saying is that every homogeneous component of that polynomial is also vanishing on that line. So if the 0 set of an ideal contains a line, what you are saying is that every element in that ideal, okay, every polynomial in that ideal is such that each of its homogeneous components is also again in the ideal of that line. Okay, so this is just a geometric reflection of this algebraic fact. So this is the key to defining what a homogeneous ideal is, and the advantage of having a homogeneous ideal is that once you have a graded ring and you have a homogeneous ideal, the quotient ring S mod I automatically gets a graded structure, it becomes a graded ring. Okay, so the key to translating from projective geometry to projective algebraic geometry to commutative algebra is that you have to change from ordinary ideals to projective ideals, from ordinary ideals to homogeneous ideals, and you have to change from ordinary rings to graded rings. So the language, instead of just looking at rings and ideals, commutative rings and ideals in them, the language becomes a language of homogeneous ideals and graded rings. Okay, that is the language that you should use, that is the algebra that you should use for projective algebraic geometry. Okay, and well, now the fact is, so let me tell you what happens. There are a few nice facts. So lemma, there is a lemma that you can easily check. The sum product intersection and radical so the sum product intersection of homogeneous ideals is homogeneous, and the radical of a homogeneous ideal is also homogeneous. Okay, so this collection of homogeneous ideals in a graded ring is it's well behaved under the operation of taking sum, product, intersection, and radical. Okay, this is a this is a very straightforward verification, algebraic verification, which I leave you to do. Okay, and therefore so we armed with this, we can now translate from projective geometry, projective algebraic geometry to commutative algebra. So let me recall that as far as affine algebraic geometry was concerned, what we did was, if you recall, we had affine space. Okay, and we have this is the geometric picture. The algebraic picture is the coordinate ring of affine space. The algebraic picture is the coordinate ring of affine space is polynomial ring in n variables. Okay, and well, you had a map like this, which is called as I, and you had a map like this, which we called as Z. And what did these maps do? Well, if you give me a subset T, if you give me a subset Y of affine space, then I get I of Y, the ideal of functions, polynomials that vanish on Y. And conversely, if you give me an ideal I here, in the polynomial ring in n variables, I get the closed subset Z of I, and every closed subset is of this form. Okay, and you know that so you get a correspondence between closed subsets here, and on that side you will have to take radical ideals. Okay, and we had things like so on this side, if you take subvarieties, affine subvarieties, which are irreducible algebraic sets, they corresponded on that side to prime ideals, which were of course radical ideals, and points here will correspond to maximal ideals there. Okay, so we had this nice translation from algebraic geometry to commutative algebra. All right, this is for the affine space. Now we are going to we can do that now for the projective space as well. All right, so so in the same way, what we do, so I'll have to make a statement here. So here is one more lemma which I forgot to mention. Probably let me mention it here. an ideal I in S is homogeneous if and only if it is generated by homogeneous elements. So this is another definition of when an ideal is homogeneous. This definition of an ideal being homogeneous requires its generators to be homogeneous. Okay, so whereas the earlier definition of homogeneity is that you take the ideal is the sum of its components, homogeneous components, and which translates to saying that given any element in the ideal, each of its homogeneous components is again back in that ideal. Okay, so this is again a simple algebraic fact that you can verify as an exercise. Okay, and the reason I need it is the following. Recall that we have defined on the projective space. Okay, we have defined algebraic sets, closed sets, as 0 sets of a bunch of homogeneous polynomials. Okay, and again, instead of just taking the 0 set of a bunch of homogeneous polynomials, you can take the 0 set of the ideal generated by these homogeneous polynomials, and by this lemma that ideal will be a homogeneous ideal. Okay, so what you will do is, so we will do the following thing. We will use this notation S of Pn. This is the commutative algebraic picture. This is k x naught to xn. Okay, so this is thought of, this is called the homogeneous coordinate ring of projective space. Okay, projective n space. See, in the affine situation, okay, we use the word A to give you the affine coordinate ring, okay, which is a number of which is a polynomial ring in as many variables as the dimension of the affine space. Now what you do is, in the projective case, the analog is the so called homogeneous coordinate ring. Okay, and you know why they are called homogeneous coordinates? Because when you write a point in projective space, these coordinates are only, when you put them together, they are only a common ratio. Okay, I mean they are given by a set of ratios. That's the reason we put a colon. Okay, a point in projective space has coordinates x0 colon x1 colon etc xn, and the colon means that there is a ratio involved. Okay, and therefore that's why it's called homogeneous, and that's why this is called the homogeneous coordinate ring. Okay, and for that matter, each xi is a homogeneous polynomial of degree 1, right? And what we do is, well, how do we start? We say closed set is of the form z of t, where t is in S, it is in this, and I'll put this h, okay, which means the union of the various degree d pieces, namely all the possible homogeneous elements. Okay, see this homogeneous coordinate ring is a direct sum of its degree d pieces. Okay, which is just trying to say that polynomial in degree n is uniquely expressible as a sum of its homogeneous components. But what you do is, instead of taking, if you take the direct sum, you will get the homogeneous coordinate ring. Instead of taking the direct sum, if you take union, you will get all the homogeneous elements, because by definition a homogeneous element is supposed to be an element in one of these pieces. Okay, so where of course SD of Pn is homogeneous polynomials of degree d in these variables. That's what it means. Okay, so you take, so what I am doing is, why I am writing it like this is, I am taking a subset of homogeneous elements. I am taking my T is not just any bunch of polynomials in this polynomial ring, it's homogeneous elements. That's the reason I have put the superscript h. Okay, and that's just gotten by taking this union, okay. And what you do is that for this T you take the 0 set of T, but now you see you are taking the 0 set in projective space, okay. Mind you, sometimes if you are working with both the affine space and the projective space at the same time, you will have to worry about where you are taking the 0 sets. You need better notation. So sometimes it's if you don't want any confusion, you put Z sub Pn of T, which means you are looking at the 0 sets, the 0 set of T in Pn, okay. And this is how the closed sets in the projective space are defined. This is how the Zariski topology is defined, okay. This was the second definition, okay. We had 3 definitions of Zariski topology. The first one was as quotient topology of the punctured n+1 dimensional affine space above. The second one is this, where the closed sets are given by 0 sets of a bunch of homogeneous polynomials, and the third is of course the topology that is gotten by gluing the n+1 pieces, each of which is isomorphic to an affine space, okay, of dimension n. So well, so this is how we have defined it, okay. And now what we can do is, well, so you have this just as in this case you have this map Z, okay, and there is also this map in this direction. What is this map in this direction? In the affine case, you give me any set Y, then you look at all those polynomials which vanish on Y, okay, and so you go like this, and then this is automatically an ideal here, okay. So I land on the collection of ideals on this side, okay. So you know I also need to put an I here, right, and you have to be careful that you should simply not say all the polynomials here which vanish on a given subset here. Mind you, if a polynomial vanishes on a subset, then it has to be homogeneous. I mean each homogeneous piece of that polynomial has to vanish on that subset. You see what we just saw some time ago was that, you know, if a polynomial vanishes on a line passing through the origin, okay, then each piece of that polynomial, each homogeneous piece of that polynomial will also vanish on the line through the origin. So it means that if you are so you must think of the polynomial vanishing on a line on the origin on a line through the origin as, you must think of it like this: take the point in projective space corresponding to that line, and that point is a 0 of that polynomial in the projective space. So what you are saying is, if your polynomial vanishes at a point in projective space, then each of its homogeneous components will also vanish at that point in projective space, and of course the constant term will not be there, alright. So if I want to make sense of a polynomial vanishing on a subset of projective space, I need to make sure that first of all that it has no constant term, and I also need to make sure that every homogeneous piece of that polynomial also vanishes on that subset of projective space, alright. So what you do is, you see finally everything reduces to vanishing of homogeneous polynomials. So when you define this I, you define it very carefully, you keeping this in mind. You define I of Y to be the ideal in the homogeneous coordinate ring generated by all f in the all homogeneous f, namely all homogeneous polynomials such that f of y is 0 for every y in Y, okay. So this is how you define. When you define the ideal of Y, you define it as the ideal generated by all those homogeneous polynomials which vanish on Y, alright. So you see, therefore this is an ideal which is generated by homogeneous elements, therefore it is a homogeneous ideal, because that is what the lemma above I have recalled says, okay. So this is a homogeneous ideal. This is a homogeneous ideal. So what has happened is, if you start with a set of homogeneous elements, you get the 0 set of that, which is a closed subset of projective space, and if you start with any subset of projective space you get the ideal of that subset, and that will be a homogeneous ideal by definition, and whatever happened here more or less will happen there except for one or two subtleties. So let me tell you what are the things that are going to happen. You know a few things in the affine situation. What do you know? You know that if I take so the Lewis-Ansatz says that I of z of I is rad I, that is one fact. Okay, then if I take z of script I of y, I will get y bar, the Zariski closure of y. So z of script I of y is y bar. Okay, and the fact is that the same thing will hold here except with one subtlety for the Nullstellensatz. So let me state it here. So what's going to happen here also, I am going to get I of z of I is rad I. Okay, and for of course I naught x naught etc xn. So and well the other thing is z of I of y will be y bar. Okay, so both facts will be true here also, except that here the ideal I start with should not be the maximal ideal corresponding to the 0 in the affine space above, because I have thrown it out. When I got the projective space below, I have thrown out, I have taken the punctured affine space and then I have gone modulo an equivalence relation, namely I have taken the lines in the punctured affine space passing through the origin. Okay, I have thrown out the origin, but the origin corresponds to this ideal in the affine space above. The point 0 0 0 0 0 n plus 1 coordinates, that corresponds to the maximal ideal generated by the variables, and this is the ideal, this is the only ideal that you have to leave out. It is a maximal ideal, but you have to forget it, and it will not so that maximal ideal will not, it is also a homogeneous ideal, it is also a homogeneous ideal because it is generated by the coordinates which are homogeneous functions, they are all homogeneous of degree 1. Okay, so it is certainly a homogeneous ideal, but the point is that it is a maximal ideal, it is a homogeneous ideal, but it is not going to come into the picture. Okay, so on this side you are only going to consider homogeneous ideals which are different from this particular maximal ideal, that is ideal generated by all the variables, and therefore this particular ideal generated by all these variables is given a very special name. It is called the irrelevant maximal ideal. Okay, so there is a name for this, x naught through xn is called the irrelevant maximal ideal. It is the irrelevant maximal ideal. Okay, and it is a homogeneous ideal, but then the homogeneous ideals we are interested in are everything except that, and that is why that is called irrelevant. Alright, it is irrelevant with respect to the projective geometry, right? And so what I want to tell you is that you can prove these statements from the corresponding statements for affine space if you just remember that the quotient on the projective space is the quotient topology given the Zariski topology on the punctured affine space above. Okay, so all these statements can be proved by translating everything to the affine space above. Okay, and by using the corresponding results in the affine case. So what you must understand is, you must understand the following. I mean, this is a picture that should help you to think of what is going on. So you see, you must always think of this is the affine space, this is the punctured affine space, and there is this projection onto the projective space. Okay, and how you should think of it is that if you take, if I draw a picture like this of the projective space, and well I take the 0 set of a homogeneous ideal here. Okay, and this is the 0 set in this is the 0 set in Pn, of this ideal. Okay, that's how closed subsets in projective space look like. Then how you should think of it is, if you take the affine space above, so in the affine space above, the diagram will be something like a cone. So it will be so this is the diagram in the affine space above. Okay, and what has happened is that for each of these lines they go down to a particular point. So this line, each of these generating lines L through a certain point lambda naught through lambda n goes to the corresponding point in projective space lambda with homogeneous coordinates lambda naught through lambda n, and this is to be thought of as simply the line above. This is just L of lambda naught etc lambda n. So you think of this point as a line above. Okay, so what you will get is, if you give me any projective any closed subset of projective space, take its inverse image here, and then the only thing that will be missing is 0, which is what you will get when you take its closure. You will get a closed subset there. Okay, 0 is the only thing that will be missed. So if you add it, you get this picture, which you can easily think of as a cone over this closed subset in projective space. So you see this thing is the cone. It's called the affine cone over Ez Pn I. This is called the affine cone. All right. So and you know, so the picture is something like this. So if you give me any closed subset of projective space and you take the inverse image in the affine space above and close it up so that you add the origin, what you get is the cone above. And what is this cone? What is it? This is actually this is none other than, this is just the z zeros of I in the affine space. It's the same I. Take the same ideal. The same ideal, mind you, the ideal is an ideal in the affine coordinate ring of an plus 1, which is thought of as projective coordinate ring, homogeneous coordinate ring of Pn. Note that A of an plus 1 is S of Pn, and this is of course polynomial ring in these n plus 1 variables. Okay, and I is sitting here. Okay, so if you start with I homogeneous here, the 0 set is a closed set in the projective space. If you take its inverse image and add the point 0, you will get the projective cone. It's called the it's called the affine cone. It's the cone in the affine space above. And what is the affine cone? It is just the 0 set of the same ideal considered as a 0 set in the affine space above. Okay, so any questions about Zi in Pn can be translated to questions about Zi in An plus 1. Okay, and then in the affine space, of course, I know I have a good dictionary. I have the Nullstellensatz sets, I have all that I need. So I use that to prove things in get statements in the projective case. Okay, so the point is, somehow already the geometry that you know, the affine geometry that you know, that kind of helps you to get the projective geometry. Okay, it controls the projective geometry. So now you see, and well, so what you will get, so there are two facts that I want to say here. You get a bijective correspondence between closed subsets and radical ideals. So if you look at this situation, the projective space and the homogeneous coordinate ring, you will get a bijective correspondence between closed subsets and homogeneous radical ideals. and in that collection you will have to get rid of this particular homogeneous radical ideal, which is this maximal ideal corresponding to the origin above which you have thrown out. Okay, so this is the irrelevant maximal ideal. So what you get in the projective case is a bijective correspondence between closed subsets of projective space on one side. On the other side you will have to take homogeneous ideals, homogeneous radical ideals, which are different from the irrelevant maximal ideal. You take the collection of all homogeneous radical ideals which are different from the irrelevant maximal ideal, that is in bijective correspondence with the closed subsets of projective space. Okay, so let me write that. Check number 1, I and Z give inverse maps defining a bijective correspondence between closed subsets of projective space and the set of and homogeneous maximal homogeneous radical ideals in S of Pn except the irrelevant maximal ideal. You will get this bijective correspondence. Okay, so the difference from the affine case is that there you simply consider radical ideals, here you consider homogeneous radical ideals, and there you consider of course all ideals, but here you consider, you leave out that particular irrelevant maximal ideal. Okay, and that is one thing. Then the second thing is of course that in this case the correspondence in both directions is inclusion reversing. It is an inclusion reversing correspondence, because as the ideal grows bigger the 0 set becomes smaller. Okay, and conversely, so the same thing happens here as well. Okay, so this is an inclusion reversing correspondence. The correspondence in one is inclusion reversing. That is also true. Then of course whatever versions of the Null-Stellen-Satz that you had for the affine case, you also have corresponding version of Null-Stellen-Satz for the projective case. What is the Null-Stellen-Satz for the affine case? If a polynomial vanishes at every point of a variety, then some power if a polynomial vanishes on the 0 set of an ideal, then some power of the polynomial is in the ideal. That is the Null-Stellen-Satz. Okay, and the same statement will work for the projective case. If you take a homogeneous but the only thing is now you have to use homogeneous polynomials and you have to use homogeneous ideals. So if you have a homogeneous polynomial which is positive degree, and if it vanishes on the 0 set of a homogeneous ideal, then some power of that polynomial is certainly in that ideal. That is the homogeneous version, projective version of the Null-Stellen-Satz. Again the projective version of the Null-Stellen-Satz can be derived from the affine version by going to the affine space above. Okay, so this is the whatever you want to do here, you go above and do it. Okay, because there you already have a clear picture, you have affine geometry already there, so you use that. All right, so let me write that. Have a homogeneous projective version, have a projective version or homogeneous version of the Null-Stellen-Satz and that is just if f is homogeneous and f belongs to I of z of I, where I is homogeneous, then f for m is in I for some m greater than or equal to 1. So this is the homogeneous version of the Nullstellensatz Satz, and so the only thing that has not been said in all this is what happens to this irrelevant maximal ideal. So that's the only thing that I'll have to tell you, and that's pretty easy to state. So so here is a fact that it's a fact about the irrelevant maximal ideal, but certainly it is not irrelevant to our discussion. So so here is a lemma which you can check. I in S of Pn, a homogeneous ideal, the following are equivalent. Number 1, I contains Sd for some d greater than or equal to for some d, okay. Then 2, z of I in Pn is empty, okay. Number 3, rad I is the irrelevant maximal ideal, okay. So these are, and this tells you why you throw out the irrelevant maximal ideal, okay. So these are these three are equivalent conditions, and if I contains Sd, then it means that I will contain xi power d for every I. Therefore rad I will contain xi, therefore rad I will contain the ideal generated by the xi's, okay. And of course there is another, there is one more possibility. It's either this or it could be the whole ring. So I should also write or S of Pn itself, right. So it can happen that see, the ideal may contain S naught. S naught is homogeneous polynomials of degree 0, they are the constants. So if the ideal contains constants, it will contain non-zero elements of the field, so it's the ideal will be a unit ideal, and therefore the radical of the ideal will also be the whole ring, it will be the unit ideal. So these three are equivalent conditions, and this is the exact reason why you throw out the irrelevant maximal ideal to get a bijective correspondence, okay. And okay, so with that we have now a nice dictionary between projective algebraic geometry and on the one side, on the geometric side, and on the algebraic side we have the homogeneous coordinate ring and homogeneous ideals there. Now let me tell you a point of surprise. We have seen for an affine variety that of course we so that reminds me, we defined an affine variety to be an irreducible closed subset of affine space, okay. In the same way we define a projective variety to be an irreducible closed subset of projective space. It will follow that by the same argument it will follow that if a closed subset here is in affine space is irreducible if and only if the corresponding its ideal is prime. The same thing will hold also in projective space. A closed subset of projective space is going to be irreducible if and only if the ideal, its ideal is a homogeneous prime ideal, okay. And the fact that you will have to remember when you go here is that under a continuous map the image of an irreducible set is irreducible. Okay, so that is a fact, that is a topological fact that you have to remember and use. Okay, so to get proof of the fact that a closed subset of projective space is irreducible if and only if its ideal is a homogeneous prime ideal. Okay, and there are two big differences. If you take an affine variety, you know that the ring of regular functions is the same as its coordinate ring. Okay, and the coordinate ring is just polynomials. Okay, and there are a lot of polynomials. Okay, there are a lot of polynomial functions. At the worst, if it's even a single point, you have you have constant functions, but if it is not a point, then you have many functions, many non-trivial polynomial functions on your affine variety. Okay. However, if you go to the projective space, there also you can define regular functions, and the amazing thing that will happen is on a projective variety, namely an irreducible closed subset of projective space, the only regular functions are constants. Okay, so that is a major point of difference between affine geometry and projective geometry. The other major point of difference is the following. We saw that two affine varieties are isomorphic if and only if their affine coordinate rings are isomorphic as K algebras. Okay, but here the projective or homogeneous coordinate ring is not such an invariant. So what will happen is you can have two projective varieties which are isomorphic as projective varieties, but their homogeneous coordinate rings are not isomorphic, which means that the way their homogeneous coordinate rings will depend on the way in which they are embedded in the ambient projective space. Okay, so of course here the definition of a homogeneous coordinate ring of projective variety is similar to the affine case, namely in the affine case you take the all the polynomials on the ambient affine space and go modulo the ideal of the variety. Okay, here also you do the same thing, you take the homogeneous coordinate ring of the ambient projective space and go modulo the ideal of the projective variety, and you get what is called the homogeneous coordinate ring of the projective variety. But the fact is that this is not an invariant of the projective variety. It will depend on which projective space into which you are putting the projective variety. So you see the geometry of projective varieties is far more complicated than the geometry of affine varieties. This is what the complication is due to. One is because there are no global regular functions which are different from constants. There are no non-constant global regular functions. That is one point of difficulty. The second point of difficulty is that the homogeneous coordinate ring of a projective variety is not, it's not an invariant. Okay, so this adds lot of richness to and variety to the geometry of projective varieties. Okay, so and that's what more serious algebraic geometry is about, studying projective varieties. Okay, so I'll stop here.